beginning of our end of last class, I introduced just kind of the start of the start of lesson 4 on compressed sensing of CT scans. And I just wanted, we had talked about a few really useful concepts at the beginning, and I wanted to review those. And so one of those was broadcasting in Numpy. And that's how Numpy deals with arrays of different shapes and kind of the rules for whether or not you can do arithmetic on them. Can anyone remind us what the kind of 2 rules for broadcasting are in Numpy? Connor?
It's like you line up the dimensions of your matrices, and they have like the same, for like a particular dimension, if they have the same number, you can broadcast them, or if one of them is 1.
Yes, exactly. And then for lining them up, do you start at the kind of beginning or end?
You start at...
Wait, Jeremy, throw it back.
I think you start at like the end, and then... Yeah.
Yes, exactly. Yeah, thank you. So yeah, those are the rules for broadcasting. Start with the trailing dimensions, which is the far right-hand side, and then 2 dimensions are compatible if they're either equal or one of them is 1. And so then I wrote a few problems as review. So suppose we have, actually, is the font large enough on this? Go up there. Okay, is that better? So we've got V, which is 3, so 3, just a tuple. M is 3 by 3, and A is 2 by 3 by 3. And so kind of before we actually run these, which of the following operations will work and which won't? So take a moment to think about these, and then we can do like a thumbs up, thumbs down maybe. Does anyone want more time? Okay, so for the first one, A plus V. Thumbs up if you think that'll work, thumbs down if you think that it won't work. Okay, thanks for everyone that's participating. Yeah, I see mostly thumbs up, and that's correct, that works. So, and yeah, V may be a little bit confusing since it's kind of just got this single dimension showing up. But yeah, that works. The 3s line up, and then we've got the 2 and 3 before. And so what's happening with that is that, it actually might be helpful to put A here so you can see 1 has been added kind of to this whole first column along both matrices, if you think of this as being like an array of 2 matrices. And then we've got 2 was added along this whole second column, and 3 was added here. Okay, let's go on to the next one. How about A plus M? And I should leave the dimensions up so you can see. Thumbs up if you think A plus M will work. Thumbs down if not. Okay, excellent. So yeah, so all thumbs up. And that works because the 3 by 3 lines up with the 3 by 3 at the end of 2 by 3 by 3. So we can do that. And there, matrix M is kind of being added to, this first matrix in A and to the second matrix in A. And then how about A transpose plus M? Thumbs up or thumbs down? Okay, great. Yeah, I see a lot of thumbs down. And this is nice. We get the error. Operands could not be broadcast together with shapes 332 and 33. Now you understand what that error means if you get it. Any questions about broadcasting? Kelsey?
How does that work? Transposing into dimensions. What do you use?
So that, and actually it's probably helpful for me to show it. So that's reversing the, let me also put, let me change this to A so we can have kind of like the visualization. So here we're taking 5, 10, 15. So basically we end up taking kind of the first column of this matrix and the first column of this one and putting those together to get this new first matrix. And then kind of second column here, 10, 20, 30, and -2, -4, -6, and putting those together. And then 15, 30, 45, -3, -6, -9, and putting those together. Let me do this again. I think it'll be clearer since we've got 3 showing up as a dimension twice. Let me do something with completely different dimensions.
In general,
Oh.
what's the rule of transposing? Like, if you get n-dimensional.
So you're, I think you're reversing the order of the dimensions. Yeah. Okay, but now I've got a 2, 3, 4, so I think this will be kind of a nice example. So when we reverse the completely reverse the order of dimensions, it becomes 4, 3, 2, and then this is what A transpose looks like. Yeah, and I definitely also recommend kind of looking at small test cases of these because I think often it's helpful to kind of visualize how they're changing. Yeah, good question. Any other questions about broadcasting? Okay, so next up, we talked about how SciPy stores sparse matrices, and that there were a few different matrix storage formats. Yeah, let's see. Can anyone describe how coordinate-wise storage works? Matthew?
Isn't the indices and then the value?
Exactly. Yeah. So you're keeping track of the index for the row, the index for the column, and the value that you want there. Great. And what's an advantage of this approach? Actually, advantage or disadvantage?
Small storage. So we have to allocate less memory or storage.
So less memory than a dense matrix.
Yeah.
Yes, yes.
And disadvantage because we cannot access the element by index that fast.
Right. So it's harder to get an entire row or an entire column.
We have to traverse to that element.
Exactly. Yes. Yeah. So if you wanted to find everything in a particular row, you would have to go through your array of row indices and pick out those kind of corresponding values. All right. And so then kind of this was an example we saw last time of, and they've used this nice color coding to show like 75 is in row 6, column 4. Over here, we have value 75, row 6, column 4. And that's how it's being stored. Right, next up is, and then this is also kind of illustrating for things like matrix multiplication. You can just, look up what you have in your value array. You're not having to go through all the spaces where you have zeros. All right, so compressed sparse row data structure. Can anyone describe what's going on with that? Look at the picture. Sam?
So to save space, the row indices are not repeated. It just says which of the n observations is the first that has that row, and they're ordered by rows.
Exactly, yeah. So this uses even less space than the coordinate sparse storage because it just keeps track of a row pointer, which, as Sam said, is just kind of telling you the first place that, or the first value that's on that row. So for row 1, the third value is the first to show up there, which is 22. And so we see that's the first value on row 1. And for, let's see what else they color coded. Row 3, the 9th value is the first there. And so you can see the 9th value is 42, and that's the first thing on row 3. So what are some benefits and or pros and cons of this approach? Valentin?
I think when you are trying to look for non-zero elements of that matrix, you don't have to go through all the non-zero elements. You can just skip row by row until you get to the row which you need.
So if you're looking up a particular row, yes, it's
Yeah,
very
fast
quick to
lookup.
do that. Yeah, fast lookup by rows. And then can you think of a disadvantage?
But by columns, it will be just the same complexity of big O of n in the worst case.
Yeah, so column lookup is painful, or yeah, more painful because you're kind of having to go backwards to calculate. Thank you. Oh, wait, throw the microphone. It's for the video. So the row pointer, great question, is telling you. So there, the index is telling you kind of where that row starts. So row 0, the first one is in value 0. So how index is being used is different for value and row pointer. And actually, it's probably easier to look at. So the first 3 values are in row 0. So you really just need to store a 0, and then this 3 lets you know, okay, now we've moved on to row 1. And the kind of starting with index 0, the third value, 22. So if you go over here, the third value is 22. That's the first thing in row 1. And then we've got 3 values here, and then value 6 is the first thing in row 2. So down here we store 6 for the row pointer. So it's that saying row 2 starts with value 6, which is 31. And then
so
continue.
the index is the row?
So for the row pointer, yeah, the index is telling you the row number. And it's telling you that, though, in terms of what the index for the value is. All right, Tim's got his hand up.
It's kind of like the way I think about this is like the values are stored in memory in 21 entries, and the row pointer is telling you the address of where the row starts. So you can think of this as like a structure, as a data structure.
Yeah, that's a great way of putting it. Like you can kind of think about like you've turned this matrix into an array of values, 11, 12, 14, 22, 23, 25, 31. Sure. And you want to keep track of where you're switching from one row to another. And so you're just kind of keeping track of, okay, we started a row here at 11, then another row started at 22, another row started at 31, another row started at 42. And so we just need a pointer to those spots where a new row is starting.
The table's a little unclear. These columns don't really mean anything here. Like they don't align with each other. Like the row pointer row only has less elements than the others. Yeah.
Yeah, actually. Okay, let me go to, you will like this table better, Terrence.
It's got colors.
So this table, okay.
Thank you.
You're welcome. Any other questions about compressed storage or sparse arrays? And so we didn't go into detail on the compressed column storage, but it's the exact same idea as compressed row, only you're keeping track of column pointers, and it's fast to look up a particular column, but in that case, it's slow to look up a row. Kelsey?
How fast versus slow are we talking?
That's a good question. I would have to look that up. Let me write that down. Something also to remember is that converting between these types is linear time. So I think generally they kind of recommend converting if you're going to be looking up a lot of rows or looking up a lot of columns. But yeah, I'll tell you the exact times next time. Any other questions?
I have this question. So, like, once we know that we have sparse matrix, and we try to decide which format to use, so, like, can we just look up for every format, like, this format is better for matrix multiplication, this form is better for, like, trying to get the inverse, this form is better for, like, to get in the transpose matrix, or maybe this form is better for multiplying matrix by columns or stuff like that.
Yeah,
so you have this trade-off.
Yeah, so yeah, different operations, and I don't know if it, I think some of the things you listed will probably be equally good in both, but yeah, it's very dependent on what algorithm you're using, and so particularly like looking at your code as well of if, if you're accessing things by row or by column in a loop, that should be a factor. And I've copied a little bit of, so here, like the SciPy documentation says that for multiplication or inversion, it recommends either CSC or CSR. So I think that those are probably equally good. But yeah, if you're doing something else where you are, looping through your rows or looping through your columns, you'd want to think about that.
Thanks.
You're welcome. Good question. And then it also says COO, I think, is a good format for constructing your matrices, since you don't want to have to be calculating the row or column pointers yourself typically. And it's efficient to convert then. So kind of use COO to pass your matrix into SciPy. Okay. Yeah, so we'll be using both broadcasting and sparse storage today. And going back to this problem of CT scans. And so I showed last time in this article that I think is very nicely written. It starts with, can math really save your life? Of course it can. And talking about kind of how CT scans work. I want to try introducing this in a different way today. So if you were actually kind of working on CT scan data, what would happen is you would be receiving some data that might look like this on the left-hand side, and you're trying to reconstruct this full picture. And the idea, and so this is, in real life, this is usually 3D. We're just going to be looking at a 2D picture. And here are the dimensions of this. This is L width for both of them, but then this is just a seventh as tall, what you started with. And the idea is, it seems clear if you did a ton of x-rays of someone, from every angle and got all this data that you'd be able to reconstruct the original, but you want to limit how much radiation people are experiencing. And so the idea is that we're kind of getting, much smaller amount of data and want to reconstruct this picture that includes a larger amount of data. So it's kind of like the opposite of data compression, in that you're kind of starting with this smaller amount of data and need to uncompress it to get the full picture. And then it's also you're having to find kind of the meaning of, kind of what these measurements, so these would be the measurements from different x-rays shot at different angles and different locations, and then getting back to, okay, what would that mean for the picture? Are there questions about kind of the setup? And so this problem, since we're using, we're going to use data that we generate for the problem, like we're going to be building this picture. It's different from a kind of real CT scan in that we first will have to make our data, then get what the measurements would be, and then we're seeing if we can reconstruct the original just from these measurements. Yeah, and so I'm going to show some pictures, but kind of what it'll look like is that an X-ray shot at a particular angle and a particular location, you're just going to get a single number from that. So here we have a line intersecting with our picture, and that would result in just one number. So kind of 1 pixel in this left-hand side of our measurements. And then this is a kind of brief review. So from the background removal lesson, that was background removal using robust PCA was written as this optimization problem. And do you remember what's special about the L1 norm? Shout it out. Yeah, it shrinks things to 0, resulting in a sparse solution, right? So it induces sparsity because, yeah, it's kind of pushing many of the coefficients to 0. And so you'll notice this picture that we'll be trying to construct is sparse. So we'll be using the L1 norm today. Okay, so the first part of this is just generating the data, and I think this uses some interesting NumPy methods that some of them I hadn't even seen before. So I think it's an interesting process. Again, if you were really working with CT scans, you're not building your own fake data set. And so here we're choosing 128 for the dimension. So this is 128 by 128. And I'm going to kind of walk through what this code is doing. So this is the whole method for generating synthetic data. And this will return kind of one square like this, but we'll walk through that more slowly. And to walk through it, I'm going to go through kind of a smaller example of just creating an 8x8 picture that has five points. And we'll see what the points mean in a moment. But that'll give you kind of the density of the data set of those white circles. So there's a NumPy method called ogrid that returns something as a column and as a row. And so here we're getting the numbers 0 to 7 as a column and as a row back. And then this is actually going to be very handy in a moment. We're going to use broadcasting with this. So we want to end up getting something that's 8 by 8. So we're kind of getting this row and column, and we can do some operations, and together with broadcasting, that's going to go from having something that is 8 by 1 and 1 by 8 to something that's 8 by 8. So it's kind of a handy trick. And so this is basically kind of like the equation for a circle. We're saying x minus a center point squared plus y minus a center point squared, and then kind of combining that with broadcasting, so the x part of the equation is still just going to be, this 8 by 1 column. The y part is this 1 by 8 row. And when we add those together, we get an 8 by 8 grid. And this kind of has a density of being 0 at the center and then getting larger as you go further away, since we're using this circular equation. Are there questions about this? Jeremy?
Can you show us what x plus y looks like? Just to get a sense
Oh,
of
yes,
what
that's a
it's
great
like?
idea. And here, since 0 is the first entry of both, you can kind of see the original x in the first column and the original y here. Okay, so now we're constructing something called mask outer, and basically that's because we're just going to be kind of interested in this center, in the kind of the center of our picture. And I think this is kind of fitting with the idea of, if you thought about doing a CT scan of someone's, someone's torso, that you're kind of getting this like circular cross section is what we're getting here. So we're just adding an inequality. So kind of taking our XY grid, and then seeing when it's less than this radius squared, that gives us this outer mask, which is kind of a ball of trues surrounded with false at the border. And this is also important, I should say, I guess, because the X-ray will be coming at different angles. Like, this kind of ensures that it's going through the same amount of person being X-rayed kind of from each angle. The X-ray's traveling a similar distance. So we take that mask. So that's our outer mask. And then we're constructing something called mask, where we just randomly generate some points in a 2D grid. And so that was a parameter earlier, kind of how many points we wanted to generate. In this case, it's 5. So we've still got something 8 by 8. And it's all zeros with 5 ones. And we can plot what that looks like. So here we're just plotting kind of each point as a pixel, 0 or 1. And we have five white boxes. We'll use a Gaussian filter then to kind of blur that. So that's kind of going around these places, but making it a bit more kind of continuous. And this is, some of this is, this is specific to kind of like we're trying to get these like globby looking shapes in our data. Here we combine seeing when, so now we've kind of gotten this Gaussian filter version, we're just going to take the parts of that are greater than the mean for it, and then also when those points lie inside that inner circle. And so that's what this is. And then actually I should maybe pull up ND image. Well, I'll come back to that in a moment. We're kind of using this additional library. Here is where we get this binary erosion feature from. And this is just picking out the middle. So kind of this was our whole thing. We want to separate that into what was the middle and what was the exterior. And so this is how we make, kind of make those globs that you saw. And this is a more pixelated version since it's just 8 by 8, whereas our original was much larger. But this, actually, let me scroll back up. So kind of this circular, or not circular, globby shape here. That's how we would get kind of the globby shapes here. Jeremy?
I was going to say it might be worth mentioning that caret sign at the end there.
Oh, yes. Yeah, the caret sign is XOR, which is exclusive OR. Actually, first let me just see where ND image. Okay, so that is a SciPy library. I'll go back to that. Yeah, so Jeremy pointed out the binary erosion gives us the inside. Really what we want is what's left over, and so we're taking an exclusive OR with kind of between this picture, the result that's everything, exclusive OR with this interior just leaves us with the exterior. And then I just wanted to pull up, because I think this is an interesting library, and we're just using a little bit of functionality from it. But SciPy has an ND image for multi-dimensional image processing, kind of as a library. So if you're interested in it, I think that would be something to check out with, with different types of filters. Are there questions kind of so far what we're doing to create these globs?
Can I have a question about this Gaussian filter? Is this something like the EM model?
Remind me what the EM model is.
So we assume that there are like a few Gaussian distributions, and then we assign probabilities to every pixel that it was derived like from white distribution or from black distribution by looking for the maximum likelihood.
I think this is more like putting a Gaussian centered at each point and kind of looking at what shape that creates.
At each point, at each pixel, right?
So we have like the 5 pixels that we've made white, and we kind of like are putting Gaussians centered at each of those and looking at the distribution that creates.
Oh, I see.
Let me pull up the documentation though. Oh, there it goes. Yeah, I guess it is like Jeremy's saying that he thinks it's like a convolution. Yeah, I think that's accurate. Oh. Like what this, actually let me grab my stylus. What this looks like in 1D would, or in, I guess kind of in 1D would be kind of like taking the points you have, and if you put like a Gaussian around each of those, oops. And then you're kind of looking at the method that covers all of these. You kind of hear about this in kernel methods sometimes, kind of like looking at where your data is and then kind of using Gaussians to construct a distribution kind of based around that data. Yeah, good question. Any other questions? Matthew?
Sorry, can you clarify?
Mhm.
Lost on that.
On the Gaussian?
Yeah.
So what that's doing, so I think Jeremy, pointing out it's a convolution is helpful. It's kind of like blurring the points around wherever we had these white pixels. So we were kind of starting with this picture, and so you could think of that as kind of doing this averaging method to kind of even out the squares around this. And so that's why we kind of have it very white in the corner, but if we take a point here and get the average of the stuff around it, that's going to be gray, whereas a point here, an average of everything around it's still going to be black. And that's a way that kind of like smooths it out.
Thank you.
Ah, you're welcome. Okay. Yeah, and we can always come back to this later too. So this is, so that's kind of just to getting that that kind of picture with the globs that in the end is going to be what we're trying to recreate. The next step is to generate the projections. And so this will be the kind of the single value that we get from shooting an X-ray at a particular angle through our picture. And so again, I'm going to walk through this, and this is something where you don't have to understand every line of the code. Okay, but more, I want you to kind of get the idea of like what the steps are. I should also, just while it's on the screen, want to highlight here we're using sparse.coo matrix in this line for our operator. But yeah, so here we're kind of feeding in what the dimensions we want it to be, and we have L as well as L divided by 7. And again, the idea is that we're using less radiation than kind of, taking it at every single angle and every single location. And so this creates, we'll kind of come back to what this matrix looks like. But we've got a sparse matrix in coordinate format. And then there is a dense method which converts sparse matrices to dense and is very useful. And that'll be helpful when we're wanting to plot what we're doing. We need to have it dense for creating these images. But the idea is that the first dimension is going to tell you the angle, and we only have L over 7 angles. And then we have L positions, so that's kind of every single pixel height. And then each image is L by L. So we're going to be getting something that's L over 7 by L by L by L. So just to kind of get a feel for this matrix, this is an angle indexed with 3, and we're kind of have it starting from 0, or just kind of position 0, and then you'll notice the positions moving and basically getting lower each time. So then this is position 1, which is really from this distance almost looks identical, but the line is slightly lower than the previous picture. Can go on 2, and it becomes more obvious if you say go to position 40. So now we can see, like, okay, we've definitely been lowering this angle, kind of keeping same angle, in this case the angle with index 3, and going to a different position. So now we're low, kind of down to 40. And then we can look at other angles at vertical location 40. So now I'm changing the first coordinate to be a 5, and this is a different angle. And actually, let me kind of show, like, if you did 4, 40, that's giving you something in between angles 3 and angle 5. And so what we have is a kind of a matrix that's keeping track of all these different angles and locations. Here we can see this is a completely different angle, the one indexed with number 15, at location 40 still. This is angle indexed with 17 at location 40. So we're kind of getting all these different angles at every possible location, where here the location basically corresponds to the height within the picture. Questions about this? And this is a little bit tricky because projection T is, it's a matrix in 4 dimensions, which can be hard to think about. So here we're kind of just looking at these 2-dimensional pictures from it by indexing the first and second dimensions, and then we're seeing everything that's in the 3rd and 4th dimension. Matthew?
Just to the recap, what is the projection again? Is that
So the projection, and we'll kind of get to that in a moment, the projection's going to talk about how we're projecting into 1 dimension, which is weird to think about, but it's going to be kind of taking this this just line at a certain place together with our whole image and just getting a single number from that. Yes. So that's representing what the CT scan gets, because the CT scan, you've got this, the cross section, two-dimensional cross section of a person, and you're sending an X-ray at a particular angle, and even though those could be represented as like a 2D picture of the X-ray and a 2D picture of the cross section of the person, you just get a single number from that, which is like the reading that the CT scan or MRI machine is picking up. So kind of getting that down to a single number.
Okay. Thank you.
Yeah, so typically, so projections are kind of something, that goes from a higher dimension to a lower dimension. I think this is somewhat unusual because I feel like people often don't talk about projections into 1D. Any other questions? Okay. So yeah, now I'm just kind of showing you can transpose, X-ray kind of going through these points. We're just going to get a single number from that. Here I've also showed just how much intersection there is. And the idea here is that the X-ray kind of going through different materials of different densities, that's going to affect the reading at the end. So it's got a sense of kind of kind of like the density of what it's passed through based on kind of what the measurement is. And so here I wanted to illustrate that, and so we get this from, so here Proj stores the projection. This is at the very beginning when I showed that little L over 7 by L matrix. This is the readings. And so here, where there was a lot of intersection, like this X-ray was having to pass through a lot of the globules, we get a kind of larger number, 6.4. And then here, we have a line kind of going off through this side part. It's not really passing through much, and we'll get a lower number. Let me find that. Yeah, just 2.1. So this is kind of how we're capturing information of how much the line has passed through. And then we're also adding, we add some noise to that. So kind of assuming that this would involve some noise in our measurements. And then this is what we're referring to as kind of the projection, this matrix, but that's just all the measurements. So it's a bunch of 1D projections coming from these lines at different angles. Tim?
What's the star Proj shape inside that argument? Like, why do you have a star there?
That's a good question. So star in Python is used to unpack list. So there's something called star args and star. And actually, let me pull this up because this is a really useful Python concept. But it's useful when you want to be able to pass, like a list or dictionary of arguments. So the dictionary, you use 2 stars.
Is that a Python 3 thing, or is that also?
No, that's in Python 2 as well. Yeah. Let me see. Yeah, and this can be useful if you kind of like have a bunch of parameters and don't know how many you'll have.
I actually find this really
Oh.
weird and annoying because, like, in some things in like parts of PyTorch, parts of NumPy, they expect a shape as a tuple, and sometimes they expect the dimensions as arguments. So in this case, the thing that Virtual's using expects the dimensions as arguments, so you have to put the star there. Whereas if it was expected as a tuple, you wouldn't have a star. It's totally inconsistent. So.
Okay, so that's true about this issue with shape, but I do want to say star args shows up other places that
Yeah,
can be
yeah.
useful.
This is where it appears all the time in NumPy.
Yeah. Actually, let me show an application I really like of star.
I didn't mean to diss star args.
Okay, yeah. I'm going to be careful about that. And are you all familiar with zip? Zip, yes. Oh wait, that's not.
I put list at the front with Python 3.
Oh,
Turns a generator.
I didn't know that. Put list at the front, like. Okay, so what zip does is you can pass it to list or tuples, and it'll of the same length, and it will go through and kind of pair them together. So here we're picking off, 1 and 4, 2 and 5, 3 and 6. But something that's kind of fun is that I'll call this C. You can undo zip then by using zip again together with star. So in this case, we wanted to pass to zip 3 things, 1, 4, 2, 5, 3, 6. And we can do that by unpacking this list into kind of the 3 tuples using star. So that's a way that lets you get your original 2 back. Okay, other questions about this figure? And that was, a great question about star args. Matthew?
So you have the value that you're getting back, you're reading, they're highlighting in the matrix.
Say that again, the values that you're
reading, I guess, like the intensity.
Yes, yeah.
And then what are the x and y axes again?
For this matrix, great question. The x-axes are the different angles, and then the y-axis corresponds to the different kind of vertical position. So when we showed how, there's a line here and then lower, that's what the y-axis is corresponding to here.
Thank you.
You're welcome. All right, so here the hard part was creating this data set, and it's actually going to be pretty quick to get back to our answer. We're going to use regression to try to recover the data. We'll start out with the L2 penalization. This is called a ridge regression. And so here we're just using scikit-learn's linear model ridge, fitting it to our projection operator, projection, and this is what we get, which is not very good. And so this was using least squares error. Now if we use L1 error, which is called a lasso regression, this is what we get, which is really close to our original picture. So this is a case where we had, very kind of like perfectly sparse data set. And so L2 regression did really poorly, and L1 regression did a lot better. Are there questions about this? Tim? Oh, okay. Tim, and then Terrence can go next.
Can you maybe do a quick just thought what's actually going on underneath it.
Okay. Oh. Okay, let me think about that one. Let's hear Terrence's question.
I was actually trying to rephrase in my mind what Tim's question was.
Oh.
Is the intensity of each pixel here sort of the sum of a bunch of polynomials derived from the coefficients we got in that long striking thing? In other words, we interpolate between we add polynomials together where each polynomial comes from an angle and a height.
Where are you getting polynomials from? Or
Well, a regression, well, I use polynomial, but it could be a line.
yeah.
We're basically adding what we see. Each pixel is the summation of what is visible from a bunch of different angles.
Yes.
Okay,
Yeah,
so
that's a good way of putting it. Yeah. So yeah, each pixel, is going to be a sum of what was seen from a bunch of different angles.
Right, at a particular height. Yeah. So
Oh.
you're combining the lines, if you will, from these X-rays. And at a particular point, you know how much is there based upon the angle and the height of the electron gun at that time. So I think that's basically what Tim's question was, that you just answered.
What? Oh. Okay. Jeremy's voting for a break. I just yeah, no, well, let me say one more thing, but then we'll take a break and come back to this. Let's take a break and we will discuss this in more detail. So let's be back in 7 minutes. So that would be 12:05. Did I start back up? And so let's talk about what's going on with this regression. And so just kind of to restate the problem. So when you have a CT scan and you get the kind of like the picture that looks like the insides, actually there's one up here, that looks like a picture of organs or tumors. That's not actually what the CT scan's producing directly, but rather, it's taking these measurements. And then, this field of compressed sensing is around how do you get from those measurements back to, or not back to, but, create a reconstruction of what the kind of the person's organs look like. So Tim asked a great question about what's going on with this regression. So we have something called the projection operator, and that's basically kind of like, if you think of linear regression being AX equals B, and you're trying to find X, in that case, so the projection operator is A. The original picture, which is this, is like our X, and then B is the measurements we got. Let me go back up here. This. And it's hard to think about the projection operator because it's a four-dimensional matrix or four-dimensional tensor. And so that's what we were trying to kind of get at up here. Go up to it. With all these plots of proj t. So this is just basically kind of like a part of A. So A is this four-dimensional matrix, and we can look at slices of it. But A represents the lines coming from different angles at different locations. So it's kind of like all the angles and locations that the CT scan's taking, and like what those look like in 2D. So let me also, actually I think I can show that down here. So proj operator dot shape. Oh, and that is also, it's been distorted. So this kind of was the four-dimensional thing. We reshaped it so it was easier to look at. But this is coming from having 128 over 7, which I guess is 18, something that was 18 by 128 by 128 by 128, and we've reshaped it here just to make it two-dimensional. But the idea was four-dimensional, that we kind of had angles by vertical location of where the X-ray was shooting, then by X coordinate, by Y coordinate of the cross section. So that's our matrix A, and then X, which we're trying to solve, is this 128 by 128 image. And so we're kind of thinking about like, okay, we put all these X-rays from different angles, are kind of effectively being multiplied by this image, and then we get out, this smaller matrix of measurements. And so we're trying to go backwards. Okay, we've got the smaller matrix of measurements, we've got all the X-ray angles. How can we get the picture of what those X-rays were passing through? Are there more questions about this? And I should say that here, like with the CT scan, it kind of makes more sense to think about, okay, what is this X-ray passing through? What we're doing, though, with the fact that it's multiplying is just kind of taking advantage of the fact that we have a lot of zeros and ones, and basically every place where either the person's organ is 0, we've got a black spot, or where the X-ray is not passing, those are all 0. And so those will 0 out. And so the only thing that gets picked up is where both of them are non-zero, and those are the intersections. And so you can kind of see, this is a different one, where they're intersecting. So if we were kind of multiplying the picture of the organs times the picture of the X-ray, that's just going to pick up the intersections because everything else zeroes out, and gives us kind of a measurement of how many locations were both of those non-zero. I have a question. So I'm using down here proj.ravel. Does anyone know what .ravel does? Is that a hand? Sam?
Just makes it into a one-dimensional array.
Exactly, yes. And I actually feel like unravel would make more sense, but it's, kind of flattening it into a one-dimensional array. And that's handy here because we're basically converting what would be a four-dimensional matrix times a two-dimensional matrix equals a two-dimensional matrix. Is kind of how I think the problem makes sense of thinking with like these CT scans, but we've converted that into a just typical matrix by a vector equals a vector. And so that's why we're having to unravel these readings just to be a, one-dimensional array. A lot of people look very puzzled, so I'd love to get more questions. Sam?
Could you explain again what the 4 dimensions are?
Yes, So the 4 dimensions, and let me go back up. The 4 dimensions are coming from our projection operator.
Right.
And so those are the angle that it's at, and we have a total of L over 7 angles, which in this case is 18 angles.
It is what?
L
over 7 is 8.
Is 18 in this case, So we've got 18 distinct angles, L positions, and that return. So this is an L by L matrix, and that's just kind of each vertical possible height is the position, and then the image for each is L by L. And so what we're displaying here is we're kind of indexing on those first two. We're picking an angle and a position and then showing the image. And so this is our way of trying to look at little pieces of this 4-dimensional array is we're just kind of, indexing on the first two and then viewing a 2D picture.
So So I guess I'm confused. Oh, I'm starting to see it. So really, we're multiplying the last two dimensions by we're multiplying the line in the last two dimensions by x, and that's giving us a single value that's like how much it's intersecting.
Yes.
But we have the first two dimensions simply because we have so many different lines at different angles, and the index corresponds to just which of those. So
Exactly.
we could just have like 3 dimensions with every permutation of the angles and the positions, and multiply it by x, and we'd still be getting essentially the same thing.
Say that again. Have 3 dimensions with the.
Since we're doing broadcasting, we're only, and the thing that we're multiplying it by is 2-dimensional. We're only multiplying the last 2 dimensions,
Yes.
but we're doing it for all of the entries in the first 2 dimensions. So it's arbitrary how many first dimensions we have. We just organized it that way. so
Yeah.
that
Yeah.
we can index it quickly.
Yes, that makes sense. Yeah. Yeah. So that's a great way of thinking about it. Kind of another, like what's happening here with the dimensions is we're actually kind of reshaping this 4-dimensional thing. I'm gonna go down to where I have it. So the projection operator kind of was, I'll just write it, 128 by, oh, no, this one's 18. 18 by 128 by 128 by 128. But 18 times 128 is 2304, and 128 by 128 is 16,384. And so what this is doing is you can kind of think of, we've turned our picture with the cellular globs or organs or however we want to think about those. That was 2-dimensional. We've kind of unraveled that into like a single vector. And then we're going to multiply that 2,304 times. Basically, like that's getting multiplied with this X-ray we have 2,304 different X-rays, you could think of it, since we wanted to take an X-ray reading from 18 different angles at 128 positions for each angle. So that might be helpful to kind of think of, you have 2,300 kind of separate readings.
So how does that relate to the previous picture, the one that was kind of wide and short? The dimensions of that?
This one. Whoops. Yeah. So this one is, actually let me write it out. This is 18 by 128. But we have unraveled this into just one thing that's 2,304 long. So kind of for each of those 2,304 multiplications we're doing, we're getting back 1 pixel here, or 1 spot in this matrix. So this is the result of doing 2,304 multiplications.
So that picture is what the CT scanner actually returns?
Yes, yeah. So this is what the CT scanner is actually measuring, but then it knows the angles and locations that it's shot the X-ray to get each of these points.
So for this picture, each row is an angle, and each column is like the position of that angle.
Yes. Yes, good questions. Other questions about this? Matthew?
And then which part of that are we regressing on?
So this is B in the regression. You can think of this as like the column on the right-hand side. And then A is, I need to fold some of these up. A is the collection of all these matrices.
But it's into a 2D matrix, right? Like projection operator is still 2D.
Yes, yeah.
Okay, that was confusing.
Yeah.
It's like,
Yeah, so it's like I think it, yeah, by the time we do the regression, it is 2D.
it is 2D.
Yes, yeah. Yeah. Yeah, I guess actually, yeah. So here we've just reshaped it as 4D to get the kind of meaning for the different points. And in its 2D form, this picture would be like a single row. So we've kind of taken this whole picture and made this is one row. This picture is another row, and so on. Because we've just kind of like unraveled that picture. And so each row is a single angle and single location, but then all the XY coordinates for that angle.
There are 18 of those.
Well, there are 18 angles, but there are 128 locations. Yeah, so there are 2,000 rows.
Okay. So I'm looking at the image you have down, the image, that's 18 rows.
All right, so yeah, so these, I should say these pictures here, these are all part of the matrix A.
Right.
The picture at the bottom, that's the vector B.
Right.
Get to it. So this is the vector B when it's unraveled.
Okay. So can you think of that as like a row, like each row of that is of the image, or?
No, it's more like each single location in this, like each pixel here, is a reading from one of those like entire pictures above.
Got it. Okay.
So kind of taking the angle at a particular location, that just gives you a single value. So that would just be one entry here.
Okay. Thank you.
Oh, you're welcome.
Leave it here in case
Oh, Matthew?
So, could we do background removal with this?
Oh,
I'm just curious. I mean, it seems like it's a line moving to a black background.
let me think about that. Are you thinking that what would be the kind of the background you're trying to remove?
Well, like if we were going frame by frame, like each frame was drawing a line through the picture. You would just the sparse matrix would become the line, and then I guess I don't know if they would compound in the same way, but
Yeah, I mean, the tough thing is you don't actually have, you don't have the picture of the line going through the globs. You just have like a single number for each of those.
and that's just the reconstruction to show it. But
Yeah. So that's kind of like the point you're trying to get to is the picture of the globs.
Okay.
Yeah. Any other questions? Okay, we'll probably review this at the beginning of next class. So definitely continue to think about it. Email me if you think of kind of other questions, because it is it's just, I think, a very different way of thinking, kind of like understanding what all the pieces are here. But it's a really interesting application of regression. All right, so let's start on, let me close these. Oh, wait, another question.
Yeah, I'm just curious. So, is that the reason we do 18 angles? Is because we can only do 18 angles to be able to capture all the projection?
Yes, yeah. So this kind of even 18 angles is enough to get like a really great reconstruction. Yeah. Whereas kind of like a naive guess might be like, oh, maybe I need 128 angles in order to, be capturing data of the same dimensionality of what I'm trying to recreate. Yeah, and there's an entire field that kind of focuses on this called compressed sensing or compressive sensing. And this is a topic David Uminsky knows a lot about.
I guess every one of those is more radiation that's going into the body, so that's why we try to reduce it.
Yes, yeah. All right, so the next lesson, continuing with the theme of linear regression, we'll be using polynomial features, so different linear regression problem. We're going to use a data set from patients with diabetes. This is kind of a classic data set from a famous paper. And it's included in scikit-learn, which is nice. And I think I mentioned it in an earlier lesson, but let me pull this up again. That scikit-learn has a number of data sets that come with it, both kind of where the data is already kind of present with scikit-learn or where they give you data kind of loading utilities that you can pull extra data in. So I think that's a nice feature. So we'll be using this diabetes data set. So we just call load diabetes to get the data. And then we know what the feature names are just from looking at the documentation. And so this data is going to have age, sex, BMI, blood pressure, and then various blood serum levels. We're going to use a train test split, which is kind of scikit-learn gives you one there. In here, you're probably familiar. Actually, I'll ask you, can someone explain why splitting into a training and test set is important in machine learning? Kelsey?
You just don't want to overfit, so you don't want to find a pattern that only exists in the training set and doesn't generalize to the...
Exactly. Yeah, you don't want to overfit to your particular data set. You're trying to come up with a model that will be general enough to handle new data, and so you want to hold out some of your data as a test set and not look at it until the end. So we're going to hold out 20% of our data for the test set, and that'll allow us to evaluate how well our model does on new data. So the problem of linear regression is AX equals B, and typically A has more rows than columns. So this would be when you have more data samples than variables. And yeah, we're trying to find an X that minimizes the L2 error, which is the sum of the squares of AX minus B. And so this is kind of assuming that our data, that there's this linear relationship between the things we're measuring and what we're trying to predict. And so in this case, that would be a linear relationship between age, sex, BMI, different blood serum levels, and the kind of long-term health outcome of the patient. So we can use, and we're using linear model from scikit-learn, has linear regression for us. So we kind of create a regression, fit it to our training set with the Y training data, and then make a prediction on the test set. And then here, I've written just a little helper method, regression metrics, that returns the mean squared error as well as the mean absolute error, kind of between the actual data and between the prediction. And so we run that and we get 75 for the mean squared error and 60 for mean absolute error. There are questions kind of on the setup, or on, this is kind of a basic linear regression so far. All right, So now we want to try to improve this. One way we can do that is by adding more features. And so we're going to try adding polynomial features. And the idea here is that instead of just having it, our outcome depend linearly on these variables, we can also look at things like age squared, or age times sex, age times BMI. And so those are the interactions between the different terms. And this is kind of letting us look for more complex relationships. And so we're just kind of going up to the squared version, but so that gets how each term interacts with each other term as well as their squared versions. And so now, and actually I should have probably put the dimensions before we start this. So we were starting with 353 rows, so that's probably 353 different patients, and 10 variables. If we add these polynomial features, now we've got 65 different variables that we're looking at. And so do a linear regression again, and we've just added, we kind of created these training features and now using those to fit our regression, and that improves our error. So we before I think had 75 and 60, now we've got 55 and 42. Unfortunately, time is squared in the number of features, and so this is going to slow us down a lot. And we can look. Let's go back up here. Oh, here's the time. So before it was 535 microseconds. And I think we've seen this before, but using % time it in a Jupyter notebook runs. So here this is doing 7 runs, 1,000 loops each. Kind of runs it multiple times and then gives you this average of how long it takes. So it's a really useful way to compare the times of things. Okay, so that was 535 microseconds. So now we're up to 635 microseconds. So it's not that much worse in this case, but it's something that's going to, on larger data sets, be an issue. Or was there also, let me look at the plus minus. What? Oh, yes, I'm sorry. So yeah, the one above was to do the linear regression. This is just to, well, okay, so this is just to create the features. To create these polynomial features. Sorry about that. And so you're having to take all the data points and multiply them together, all possible pairs, and doing that calculation just to even create this set of polynomial data is taking even longer than it took just for us to do the linear regression, but we're still going to have to do a linear regression on this new data set. So this is kind of a time concern. So it's something that has, improved our error, but it's going to slow us down. So we're going to look at a way to speed up the feature generation. First, I should stop. Are there any questions on how the polynomial features allow us to kind of create a better model than the plain linear regression, but then they take longer to calculate? Okay, so we're going to use Numba today, which is a Python library that compiles directly to C. Jake Vanderplas has some nice tutorials on them. And I like in this tutorial, he says that a lot of people ask him, isn't Python pretty slow? And he's kind of got an answer of why he likes, and Jake Vanderplas, I should say, has a PhD in astrophysics and works at the University of Washington, has like a Center for Data Science. And he's a contributor to a lot of Python scientific packages and does a lot of speaking. And also, I think, helps run like University of Washington's kind of like at their Data Science Institute. They have like, data science for social good, summer programs and things. But he goes through kind of reasons why he likes having a Python implementation as opposed to just, doing the whole thing in Fortran or C. And it's, Python code is easier to read, understand, and contribute to. Pure Python packages are easier to install than Python wrapped C or Fortran code. It's easy to use at scale. So I think these are kind of some good arguments for why you would want to maybe compile some of your Python code to C as opposed to just switching to C or Fortran completely. And Numba is one way to do that. So from Numba, we're kind of importing a number of methods and decorators and types that I'll kind of talk about as we use them. So we're going to step back from the problem of this linear regression or polynomial feature generation and just talk about what Numba is and how to use it and kind of go through a sample problem. So Numba is going to allow us to kind of avoid memory allocations and copies and give us better locality. So we're going to start with kind of this toy example. So this is something just in plain Python and NumPy where we have some number of observations that we're looping through. We've got two different arrays, x and y, and we kind of want to take each value in x and y, do some computations on them, and then store them in array z. So this is just a process in Python. Notice since we're using NumPy, we can give ZZ a type. This says, or I'll ask you, do x and y have types here? And actually this is confusing because I named these variables x and y. Do x and y inside this inner loop have types? Does anyone want to make a guess? So Valentin's suggesting float 32. So for our arrays, x and y that we're passing in, we have float 32. And ditto for ZZ, where we're going to put our result, we have float 32. But here inside the loop, we have these kind of just temporary variables, x and y we're using, and those don't have specific types. So even though they're actually we're always going to be putting float 32s in them, Python doesn't know that. And that's kind of one of the things that, so Python is not a typed language, but in typed languages like C or C++, you have to say, what type of variable it is when you declare it, and that, lets it know how much memory to set aside. And so it's kind of better for optimization, although some people prefer that, Python is flexible and you can give it different types and not have to declare it. So here we're timing this time to just kind of take in our two arrays, go through each of them, do all these operations, and create an output. and that's taking 49 milliseconds. So this was kind of the worst version. What would be a way, before we even get to Numba, a way to improve this? To speed it up.
We can try to avoid
Oh wait, Jeremy, throw the microphone.
we can try to avoid the for loop and vectorize,
Yes.
hoping that the hardware will make it in parallel.
Yes.
Try to locate more.
Yeah, so this for loop seems like a bad idea because it's like we're individually going through, each pair of elements in the arrays, and we're doing the exact same thing, but NumPy lets us vectorize that. So we can here take out the for loop altogether and kind of just do the operations on the entire matrices, thanks to NumPy. And so if we compare, this was 49 milliseconds. This is 35 microseconds. So notice that's over 1,000 times better. The units have changed from milliseconds to microseconds. So that's a big speed up. So that's really great that NumPy lets us vectorize. Does anyone remember the other kind of technical term or buzzword that we often say along with vectorize? It's actually an acronym. Louder? Yeah, SIMD. So single instruction, multiple data. So that's what NumPy is letting us do here, because we are doing the same instruction on all these different entries in X and Y. So now Numba has something called a just-in-time compiler decorator. And in Python, decorators are kind of these methods that are applied to functions to kind of alter how your function works, that show up with an @ sign above the method. So this is pretty simple. So we imported JIT from Numba above. And again, JIT stands for just-in-time compiler. And we just add JIT on top here. Apply it to, so we've got our for loop back. So this is kind of, or this is the code from the top original Python process. And what this does is, so we're no longer vectorizing, but we do have better locality here. And now when we run it, we're down to 6 microseconds. So the version with NumPy was almost 36 microseconds. So this is 6 times quicker. And then the one in plain Python with the for loop was really slow. That was like 50 milliseconds. Does anyone want to say what does it mean to have better locality? I kind of learned about this with Brad.
It means that the memory is stored closer on the device.
Yes, yeah. So it's you're accessing data that's close to each other in memory.
Register or something as opposed to RAM.
Yeah, I mean, so it's often, you can talk about time locality or space locality, but it's kind of using things that you access, kind of like when you access, something, use it multiple times before you write it back to slow memory. So kind of like while you have it in fast memory, like do all the operations you need with it, as opposed to writing something, or carrying something from slow memory to fast, using it, taking it back to slow, bringing it to fast again, using it again, trying to consolidate all those uses, and then, and using things next to each other.
Okay.
Great, thank you. And so here, I think it can seem maybe kind of counterintuitive that we've put the for loop back in. But the idea is that we're kind of, we're picking up x and y, which we need, and then we do a bunch of operations with x and y. And this is, this is kind of a toy example, but you could have a more complicated algorithm where you are, using them multiple times. What would happen if we were doing this in NumPy without the for loop? So kind of this example up here potentially has poor locality. Why is that? Sam?
In that loop, that function, you're probably reading in x and y into the cache over and over again at every step. But in the C++ version, they're probably doing the operations on one part of the array at a time, and then writing it to Z and then getting the new part of the array.
Yes. Yeah. So the issue with the NumPy array is if you want to do something on all of x, maybe all of x doesn't fit in cache, and so you're pulling in part of it, doing the operation on that part, then you have to pull in the next part of x, do the operation on that part, pull in another part of x, do the operation on that part, and then you go on to the next line and you're like, oh, I need the first part of x again. This is, if x is a really long array. Yeah, thank you. Are there questions about this? These are kind of getting at the concepts we saw back in week 1 with the Halide video. Okay, so let's go on to make this even a little bit better. Numba also has a vectorized decorator. So here we're using Numba instead of NumPy. So at this one, we use the just-in-time compiler decorator and kept the for loop. Now we're taking out the for loop, just have the vectorized decorator, and it's actually it's almost equivalent to using the just-in-time compiler, which was 6.4 microseconds. This is 5.8, but it's kind of good to know these two different options. Tim?
What's the difference between Numba's vectorized and just NumPy's using NumPy vectorization?
So this is still compiling to C, so it's still optimizing what happens. So it's not doing like with NumPy where it's doing this having to use all of X, so it's might pull the first part of X into cache and then pull in the second part and then pull in the third part, and then the next line it has to use X again, so it starts again with the first part of X. Numba has optimized that away, so it's not gonna do that sort of thing. And the reason Numba's able to do this is because it's compiling to C. So Python, when it's running dynamically, it doesn't know that, oh, I'm going to use X again in the next line, and so this is kind of wasteful that I'm pulling each section into cache and then putting them back when I'm going to have to do that again one line from now. Whereas C is able to optimize things like that, and so that's kind of what Numba's getting you, is this kind of big picture optimization.
Doesn't NumPy also use C though when you do vector operation?
NumPy does use C, yes, that's true, but that's kind of on an operation scale, whereas
So this Numba completely compiles the code almost into C?
Yes, yeah. Whereas here, even though NumPy, is using C on an operation scale, you still it doesn't have this knowledge between lines of hey, I'm using X in this line, but I'm about to use X again in this very next line. Yeah.
I'm just looking at we wrap this in another decorator for just in time? Like, could we also just in time the vectorize, or would that not work?
I'm actually not sure about that. I think they recommend just using one, but I can look at that.
There are 2 ways to solve this.
What?
There are 2 ways to solve
Okay,
this.
sure, yeah.
Oh, using
So you have to use vectors to do the same.
what? Okay. Oh, thanks. Good questions. Okay, yeah, and actually, I guess in the interest of time, should probably stop here. So next time we'll be applying this to going back to our problem of wanting these polynomial features, but wanting to be able to create them more quickly. I also wanted to remind you that Thursday, homework 2 is due, and so is the draft of your writing assignment. Tim?
How are you defining a draft? Like, what's a draft?
So, I mean, the better shape your draft is in, I think the better feedback you'll get, which will make your final better. But it should be, I guess, like reasonably complete. All right, any other questions? All right, I'll see you on Thursday.